In this video, I'd like to talk about a very important series called the harmonic series. The harmonic series is defined as the sum, n goes from 1 to infinity, of the ratio 1 over n. If we write out the first few terms, we'll see that this series, the sum, is the sum of 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. We see how this is working now. And so as the n gets larger and larger, the terms that are being added to this series are becoming smaller and smaller and smaller. But we still have to ask the question, does this series converge or diverge? And this is going to be a question that we ask very frequently moving forward. Converge or diverge. Remember, a series is said to converge if it adds up to a finite number, and we've defined this in a very systematic way. For every series, we can define a partial sum, or a sequence of partial sums, S sub k, which add up the first k terms in the series. So this is the sum, n goes from 1 to k, 1 over n for this harmonic series. This is 1 plus 1/2, etc., all the way up to the number 1 over k. But that's it. So that's the partial sum, S sub k. And we can make a sequence of partial sums, S1, S2, S3, etc., up to this term Sk, and beyond as k goes to infinity. And remember that our series converges, so our series adds up to a finite number if and only if this sequence of partial sums converges. So for every finite number k, the partial sum is well defined. It's a finite number. It's a sum of finitely many numbers, so of course it's finite. And the question is, does this sequence of partial sums have a limit? So does the limit of S sub k equal some finite number? This is our question then. It turns out that for the harmonic series, the limit of partial sums is not convergent, and therefore the harmonic series is divergent. So I'll write this down. The harmonic series, sum 1 to infinity, 1 over n, this series is divergent. So let's show it. Remember, what we have to show is that if we believe that this is divergent, what we have to show is that the limit of the sequence of partial sums does not exist. Or maybe equals positive infinity or negative infinity, something like that. So we need to consider this limit. So the method that we'll use to show that this series is divergent is we'll actually look at a subsequence of the partial sums. We won't look at all the partial sums. We'll look at a subsequence that goes off to infinity itself. And if we can show that that diverges, then that'll be enough to show that the entire sequence diverges. So this is our sequence of S sub k's, our partial sums. What we're going to look at for this example is the subsequence of terms of partial sums who are indexed by a power of 2. So in other words, we'll look at S1, we'll look at S2, we'll look at S4, so we're going to skip S3. So from our sequence up here, we can write down the ones we're looking at. And then we're going to skip a few more and go to S sub 8, and then to S sub 16, S32, etc. And of course, as k goes to infinity, this subsequence also, the index also goes to infinity. And so if the limit exists, so if S exists, the limit of the sequence itself exists, then the limit of the subsequence has to be the same number. So the limit of S sub k would equal S, which would be the same as the limit of this S sub 2 to the power k. All right, and so what we're going to do is show that this limit right here does not exist. So let's write out the first few terms. S1 is just 1. It's just the first term. S2 is 1 plus 1/2. And then S4, I'm going to write this one slightly differently. So S4 is S sub 2 to the power 2. That's 4 is just 2 squared. But this term, this partial sum is the sum of the first 4 terms of the series. So it's 1 plus 1/2 plus 1/3 plus 1/4. And at this point, we can group these two together and notice that 1/3 is bigger than 1/4. Okay, 1/3 is bigger than 1/4. So what I can do is replace this term, if I make a greater than symbol here, I can replace this by 1 plus a half plus, and instead of a third, I can write this as a quarter plus a quarter. And of course, 1/4 plus a quarter is itself a half. You add up 1/4 plus 1/4, you get a half. And so our sum, S sub 4, is bigger than 1 plus a half plus a half, or 1 plus 2 halves. And I'm going to leave it written this way, even though we know that that's just 2. I'm going to leave it written like this. Let's go to S sub 8 and see if we can do something similar. Try to notice a pattern here. So I need some clean paper. S sub 8 is S sub 2 to the third. 8 is just 2 to the third. And this sum is 1 plus a half, plus a third, plus a quarter, plus 1/5, plus a sixth. You can see how this is getting tedious, plus an eighth. But we're going to apply the same mode of reasoning. So what is that? Well, we've already talked about this 1/3 plus 1/4 can be bounded by a half. But let's look at the next 4 terms. 1/5 plus 1/6 plus 1/7 plus 1/8. Of all these 4 terms here, 1/8 is the smallest one. So if we replace each of the preceding 3 by another 8, 1/8 instead of 1/7, 1/6, 1/5, we will make our sequence larger. Sorry, smaller. We'll make our sequence smaller. So our sum. So this is then 1 plus a half. If we swap this out with a greater than symbol, again, we're going to replace 1/3 by a fourth. So here we have 1/4 plus 1/4. And then here we're going to replace the 1/5, 1/6, and 1/7 each by an eighth. So we've made our sum smaller. Okay, and then we notice, just like we did before, that a quarter plus a quarter is a half. And here with this group of 4 1/8, well, 4 times 1/8 is also a half. And so what we have now is that our sum, S sub 3, S sub 2 to the third, I should say, the 8th term in the partial sum sequence, this is greater than 1 plus a half plus a half plus a half, which is, of course, 1 plus 3 halves. And now we start to notice a pattern. So notice that what we've bounded this by, S sub 8, so S sub 2 to the third, is greater than 1 plus 3/2. Let's go back and look at the ones that we did before. S sub 2 to the 2 is greater than 1 plus 2/2. S sub 2 to the 1 is greater than 1 plus 1/2. And 1, of course, is 2 to the 0. This is equal to 1 plus 0/2. So these first two are equal. After the first two, we get greater than. And it turns out that you can continue this process, and you should work this out. So try this for S sub 16, which is, of course, S sub 2 to the 4. So you should do some work. You should get that this is greater than 1 plus 4/2. And in general, the partial sums, when the index is a power of 2, so S sub 2 to the power n, in general, this is always going to be greater than, or equal to, we'll say, if we want to include 1 and 0 in this mix, 1 plus n/2. All right, so we've shown the general method of how to do this. When you do S sub 16, you're going to get exactly what we had for S sub 8, plus you're going to get 8, you're going to have 8 copies of 1/16 here. And that's how you're going to get the half for that part of it. And so this is now a bound, a lower bound on our sequence as n gets really large. And let's take a look at the limit then. So remember, what we want to compute is the limit of S sub k, the partial sums. And we've already agreed that if that limit exists, then it's going to be the same as the limit of just the powers of 2, the index terms that are powers of 2. But what we've just found is that this limit has to be, so these partial sums are greater than 1 plus, in this case I called it n, but k/2, and this is a limit as k approaches infinity. Okay, so I'm just replacing S sub k2 2 to the power k with this term that we've bounded it by in the previous pages. And of course, as k gets very large, 1 plus very large is very large. This limit diverges. Okay? And since this subsequence of partial sums diverges, the sequence of partial sums itself must also diverge. And so what we conclude is then, therefore, even though this series appears to be extremely nice in the sense that the terms are getting smaller and smaller and smaller as we add more and more of them, this series diverges.